The premium. This is good.
I love my favorite. This is like, that was a better.
That's why you
It's
so much money to it on my. Yeah, I think the real basis. I know, right? You gotta roll. It's either color based, like the home is the story, but the most important nature of us. I mean, it's trying to have a stop. Yeah.
Now, I started getting a little TikTok game.
Great, can you guys hear me online?
Hear me online, okay? Okay, how about now? Can you hear me better now? Or is there still an echo online? Okay, good morning. Hopefully everybody is doing well. Sorry. So last time we talked about definitions such as instantaneous. What does instantaneous mean when you're talking about an instantaneous signal? It's what? Okay, it's dependent on time, but it's also like that I of t, V of t. It's just the signal that we found in the past. So that's what we've meant by instantaneous, is those signals that we found in the past. So it has varying frequency, yes. So it would be considered something in the AC domain. So when you talk about instantaneous, it means that it has frequency component to it, and it is all of the signals that we've really defined in the past when we found a VFT or IFT. Right, average, what does the average mean when you talk about an average of a signal? Anyone?
Like average of one period,
Okay.
or like, I don't know, I'm gonna say what that was the word average. Like,
Or maybe I'll say over one period. All right, so that's something to note about that is particular. It's only over one time period. So you just take it over one time period. And it is the middle, if you want to use the middle position of a signal. So it would be, if it's a sinusoid, it's right in the middle of that. If it goes up the same and down the same, it's exactly in the middle of that. So if it's not a sinusoid, it's hard to kind of define. And so we use this definition where you integrate the area and then you take it over the time period of it, which gives you the average or that middle point in the signal. And then RMS value. What does RMS value mean?
Isn't it like on a theoretical level, it's essentially turning the AC source, like finding the value of the AC source as a DC value for various, or to find various other values like power.
Yeah, it's basically a way to model from AC into the DC. And so it is a definition so that we can find things such as power. And this came up because if you find, like, try to find the average or use the average to find the power, and you think about a sinusoid, that average is going to be 0. But you know there's power really there. And so this is a way to relate and find a value in AC so that it can be similar to what we know in DC of an actual value. All right, any questions about these? So again, these are going to be equations that you either just need to memorize or just have very handy and know where to find them. And last time we went through examples to find the average of the signal and RMS value of the signals. And so today we're going to move to, I started going into the definitions of complex power. And we're going to expand on that going forward. So we did go through that power has different units to distinguish them, even though they really are watts, which is volts times current. In power, in complex power, we're going to use volt ampere to define the complex power. So it differentiates it from just the normal DC power. And as part of that, then complex power has 2 components. P average, which is the real part of it, which would be more of the relationship to DC power. And then you have the Q, which is in the imaginary part of the complex. And that is, sorry, called the reactive power. And that is defined with VAR, which is a volt ampere reactive, to distinguish it in the complex domain. So that is the 2 other units that you kind of just have to know. They all mean the same thing, they're watts. But to differentiate and just distinguish them, they use those different terms when you're talking about power with them.
So what's the difference between volt amp and volt amp reactive? The I or the J?
So volt amp ampere is referring to the whole components or both components of complex power. So it's the combination of both the real and the imaginary portion.
And then both have reactive is just the, like the J portion.
Correct, just that imaginary portion only. And then when you talk about complex power in watts, you're only talking about the real portion of it.
When we deal with complex power, are we typically in a Cartesian form or are we gonna switch to
Yeah, so most of the time. So it depends because a lot of times you're just looking for the magnitude and then you would look at, is it the magnitude of the real or the magnitude of the imaginary? So you're going to look at them kind of separate and we'll go through examples of what you'll see. And then you'll look at it. So complex power, you're going to want to look at it in Cartesian because the real portion is the average power. And then the imaginary portion is this reactive power, which they just mean different things. And so it will depend on when you want to use it. So we'll go through examples and hopefully that will make more sense. Yes.
So why is it divided by 2 on the IMS and the VMs?
So VM was defined as V was VM with, so this was in polar form. So the VM e to the J theta V. And I don't have it on here. Backwards. So this had to relate to Z. So Z here is B over I. And S was defined as, oh, here. I didn't do it there. S is defined as a half of V times I complex. And the complex conjugate of I just means that you take wherever the J is and you make a minus of the J. So when you're looking at this, I in this case is going to be well, this is kind of more confusing. Yeah, let me just ignore this portion. Let me go back to just this. So S, and then when you plug in S, you're going to have a half of VM. And so this ends up being a half VM. And when we change it back to the time domain, we get and then we define the VM RMS and IRMS just so that we can get that form is the same as just VRMS times the I conjugate of RMS. And so that's where the 1/2 is 1 over square root of 2 times 1 over square root of 2. So in order to get this term of the halves here, what did I forget to write a half? Sorry, I forgot to write a half here. So to get the halves in this, it's 1 over the square root of 2 times 1 over the square root of 2 to get that half. And so those are just a new definition just to match that form so that we get that S times VRMS times IRMS. I conjugate RMS. Yes.
For the second row, underneath the half BI asterisk, is it, you've got 1/2 BM e to J theta B times e to the negative J theta I, that's supposed to be times I in there, or is I not included in that second row?
Nope, it should be. I just didn't write that again. I can just erase this portion too. It doesn't matter if you move back. Those were just to get the other, anyway. Okay, so here it should be, oh my goodness. Yeah. Thank you. Okay, I am VM. And so to get this half is just 1 over the square root times 1 over the square root of 2. So that's why you need the halves in there.
Were those like rows underneath it, was that just using Euler's to convert? Take it out of the exponential?
Those were to get, yeah, I just changed it back into the rectangular form.
Yeah.
So
Euler's formula?
I don't know if it's Euler's, just this one. So it's just translating it back into the
Okay,
Cartesian from that polar form.
okay.
So the real portion of it was the magnitude times cosine theta, and then the imaginary is the magnitude times sine theta. So that's all it was. It was just writing it in a different form, but I realized it doesn't matter for what I was trying to explain. So I left it in, it's fine to look at it in the polar form still. So that's where those 1 over square root of 2. It's just to get that definition to match the equation of this imaginary or the complex polar. I can't talk today. Complex power. There we go. Okay, I can really talk. Okay, yeah. So this right here is just the same thing, except for it's in rectangular form. All right, so a couple other definitions. Apparent power is where you take the magnitude of that. So the magnitude of the complex power is now apparent power. So this is a new definition. And then we now also have what is called this power factor, which is going to be this cosine form. And we're going to see in a little bit why you want this power factor. Helps you understand just more about the circuit characteristics. So these two new definitions that you need to also understand and know. And then you also need to understand that the average portion of this is that real portion of the complex. And the reactive power is that complex portion where it's with the J, so the imaginary part of it. So those are new definitions, and then we'll hopefully get to understand them more as we go through examples. All right, any questions so far?
So power factor is the average divided by the complex, divided by complex power, not by the max.
Correct, yes.
Okay.
Yeah. Well, it's So never mind. No, let me take the, with the, it's, yeah, never mind. So the power factor, so the power factor, as I said, leads us to more information about the circuit itself. So for different loads where you have complex load again. Sorry, online, you have a question. I'm not quite sure what your question is. It says, where is 2 coming from? So I don't, V and I. Still not quite understanding what your question is as far as over square root. So these equations, again, are just to match this equation here. And so this is the form that we want of that complex power is the term VRMS times the complex conjugate of IRMS, since that is, you know, the definition of what we've known for power is I times V. So we're just relating those and defining these as new definitions for VRMS and IRMS. And so in order to get the 1 over square root of 2, we're using this from this definition of complex power. And that's just a given to us of what the complex power definition is. Okay, hopefully that answered your question. So power factor leading and lagging relationship for a load Z. So this was the power factor angle which is the angle portion of that power factor. And so if that power factor angle is 0, we have, we know that it's purely reactive or purely resistive, sorry, purely resistive. And so X must be 0 in that case. So you only have R. So you only have a real, you have no complex. And then your power factor in that case will be, wait, cosine of 0 is 1. Sorry, I think I said that wrong. So if theta V minus theta I equals 0, then you have a power factor of 1. So you only have purely resistive, and I is in the same direction as V. So remember, let me go back to this one. So remember this diagram that I kind of showed last time. So what I'm saying there is that when you have only real, these two are going to be in the same direction. So that's what that is referring to. And then if theta Z, if that is positive, that means that the theta V, which is your voltage, is greater than your current. And so I lags V. And then if theta Z is 90 degrees, that means that you are going to just have purely inductive, and you again have lagging. So we're in this. And then if it's negative, then you have a capacitive. And you have I leading V. And hopefully those make more sense by looking at those diagrams. So current is first, you would be leading. And if it's voltage, or if the current is negative, then you're in the lagging. So that helps you determine, you know, just from the values that you get from this, where are you? Are you leading or lagging? All right, so first thing we need to do is kind of look at determining just from the expressions themselves, how do we find that complex power? So we've analyzed the circuit. We have now our V of t and I of t, just like we've done in the past. And so these are after we kind of have a result for those. How do we find that complex power? And so with complex power, we have complex power, apparent power, average power absorbed, reactive power, and power factor. And the power factor helps us to know, are we leading or lagging or et cetera. So love that my window's shut. So to find first, we're gonna find 818. Sorry, I'm pulling up the solution again. It closed on me. Okay. So first we're gonna do is for A, we wanna find that complex power. So to find complex power, we need V RMS and I RMS. Conjugate. So what is V and what is I? So we just can change this into the phasor for V. So for A, what will this phasor be? You guys remember how to change to phasors?
110 and then exclamation.
Yep. So you take the magnitude portion, and that's the amplitude, and the angle portion is going to be the angle in the J. So it's the amplitude of your cosine. Note that you have to be in cosine form. And then you take the amplitude E raised to the J of theta. So what is the I phasor? Yep. Correct. So we have the phasors. So now we can just take, use that definition of VRMS, which was 1 over the square root of 2 V. And then IRMS is just 1 over the square root of 2I. So this is just 1 over the square root of 2 times 110 e to the minus j 60 degrees. And this is 1 over the square root of 2 4e to the minus j 25 degrees. And so the complex power is just multiplying those, except for we need to take I conjugate. So it would be 1 over the square root of 2 times 1 over the square root of 2 is 1/2, and then 110 for, oh, oops, I put 2 e's in here, sorry. And then we can add these because they're being multiplied. Well, I'll write them down first. So this ends up being 220. And then you're going to add those two together. So 60 plus 25 for a minus 85. Or no, minus, sorry, it's a plus. Wait a minute. Sorry, this should be the complex conjugate. So sorry, that should have been the complex conjugate of I, so that was a positive. And so that is negative 35. So the complex conjugate, you just take whatever J is in the equation and make it a opposite J. So IRMS is 1 over square root of 2, 4e to the minus j 25 degrees. So the J portion is just that minus J. Yep. So you take it to a plus J. And so this is our complex power in polar form. So apparent power is going to just be, I don't think I have apparent power. Okay, average power, is going to be the real part of this. So we need to change it from polar to rectangular to get that. So to find the real portion of this, how do we change that to rectangular form? Yeah, so it's the magnitude. In this case, the magnitude's 220. And then cosine of theta, which is minus 35. So this ends up giving us 180.2. And what's the units for this one? Watts, correct. All right, the reactive power is the Q portion, which is the imaginary part of S. And so that's going to be the magnitude times sine of the negative 35 degrees. And that ends up being minus 126.2. What's the units for this one? Correct, VAR. And then the power factor is going to be the average over the magnitude of the complex. And so 180.2 over the magnitude of the complex there, you can see is just 220. So you have to have that one in complex form to find that value. And that ends up being 0.819. So what does that mean? A 0.819 means that it's leading.
Which formula did we use for the power average here?
So to get power average, you change this from polar form to rectangular form. And that is the magnitude times cosine theta to change back to rectangular form. Yes.
So your nomenclature for power factor is a little different than what was given above. So that S in power factor is just the magnitude of just the magnitude of the complex portion.
Yeah.
Okay. Thank you.
All right, yes.
Do you care if we do decorations, like we get those lines like two angles, or do you want us to do it with the average?
So this one is what's going to actually tell you more information. So this will give you the actual, I mean, yeah, this one. This is the one, you want an actual number to say, am I leading, lagging, or am I only resistive? So,
If you did like these first second, they could just have the do your calculations with the actual values.
Yeah.
So is the apparent power always equal to the amplitude?
yeah. So you would say this is the apparent power, which is 220, which is the magnitude of the polar form. Does that make more sense? Okay. Other questions? Yes.
Show again why is leading power factor.
What
Why
is,
is leading power factor? Just show. Yeah. Point A, one, right?
yeah. What is,
Why is leading?
oh, because it's less than 1.
No, I mean, why the power factor is leading in this case?
Because you're less than 1.
Less than one.
Okay. Okay, why don't you guys work in small groups to find the complex power, apparent power, average power, and reactive power and power factor for part B here. $200 for Q. So I'm not sure what 200 you're referring to. I only used 220. Oh, I see. Another typo. Sorry. 220 should be that one. Sorry, thanks. Thanks for pointing that out. Yes, that should be 220 sine minus 35 degrees. And that's. So to answer your question online, the frequency doesn't change any of the complex information. So it basically does not, so it doesn't matter what frequency you're at. Okay, and then you only use the complex conjugate for the current just due to the definition or equation for that complex power. So you just use the current complex conjugate. All right, backing up to Eddie, I misspoke when I told you where that leading came from, and I realized after I said it, it's not the value of the power factor, it's actually theta V minus theta I. So you look at the power factor angle, and in this case, theta V was 60 or minus 60 degrees. And then theta I, which is the angle of the current, is minus 25. So when you take the theta V minus theta I for that power factor angle, having it be negative, it puts you here, which tells you the I is leading V. So that's how you find if it's leading or lagging. I was like, wait, it has to do with the power factor, but it's power factor angle. So I just kind of skipped through that. All right. Have you guys been able to get these answers? Is everybody done with this yet or still working on it? Show of hands, who's finished? Okay, looks like maybe the majority of you guys Okay, let's go through this. So complex power, we're gonna have 1/2 times 12 times 0.4 e to the j 30 minus 15. Yeah, oops, EV. Plus 15. So again, that complex conjugate. And so this ends up being 12 times 0.4, 2.4 EJ to the 45 volt amps of volt ampere. And then the average is 2.4 cosine 45, 1.7 watts. And Q is 2.4 sine 45 for 1.7 volt ampere reactive. And then the power factor is 1.7 over 2.4 for 0.707. And then theta V is 30. And I is minus 15. And so theta Z is 15. This is lagging, but that would be leading, right? No, it is lagging. Okay. Lagging.
Power factor has no units on it.
Correct. The power factor is unitless. All right, any questions on this? Yes.
So when you're finding the power factor here, we have on the table, it gives you the formula theta Z equals theta V minus theta I. Just curious right here. We have theta here minus theta. Now, 45 degrees.
Yes.
Yeah, sorry. Theta V minus a theta I gives you a 30 minus a minus 15 for a plus 45 degrees. So it would be plus 45. Yes. Sorry. I am making lots of errors today. Thank you for catching those. Other questions? The angle opposite. Okay, so yes, the question online is, okay, you look at the table here. And for this one, you see that it's between 0 and 90 degrees. So therefore, you have inductive. And so you're considered lagging. Yes.
Will we ever have a degree that's greater than 90?
So say that again, if,
So like, will we ever have a resistance that's greater than 90?
no,
No.
no. So it's either gonna be 0, plus 90, or minus 90, or somewhere in between on that right side of the plane. So real value can never be negative because it's coming from a resistor. So you're only in that first half of the imaginary plane. So that's why you can't hit any angle greater than 90 or negative 90. All right, any other questions? Okay. Gene. Okay, I am just going to put the solutions on here for exercises for you guys to be able to use. And then if we have time, we'll kind of come back to them to go through more. Yeah, I can get there. F. Okay, so the next topic that we're going to move on to is maximum power transfer. And so for maximum power transfer, I wanted to just go back to looking at this with just resistors. We would have a circuit like this. So any complicated circuit, we can reduce down to the Thevenin equivalent, which is just an RTH and a VTH. And that can model any circuit. And then if we put just a resistive load on here, and we look at the power of it, we would have the voltage across the L times IL will be your power here. And IL is going to be, VTH, well, I'll use VS, sorry, because the other equation's in VS, over RS plus RL. And VL is IL times RL. So this can also be written as IL squared RL. So if you remember, I don't know where you guys learned this, but if you take the derivative and set it equal to 0, this gives you a maximum of the graph. And so what we like to see is that, we want to supply as much power to the output as possible. So therefore we want to find the maximum power we can transfer to this load. And so taking that derivative and setting it equals to 0 is this equation right here. And so in order to combine these, I would need to get a common denominator, which means I'm going to have one more RS plus RL on the first component. I cannot. Vs squared over RS plus RL square or cubed. All right, so I combine these and set those equal to 0. This is going to multiply over to the other side to give you 0. And then also the Vs squared, multiplying it over to the other side gives me 0. So then I'm left with RS minus RL equals 0. And so this is the maximum when RS equals RL here. So for the maximum power transfer for a purely resistive circuit, I would just design this so that this RTH or RS is equal to RL. And that would give me the maximum power transfer I could have. Yes.
The power of the VRL, that first derivative equation, essentially when it equals 0, basically what it's saying is that if you look at graph of the actual power, that's when it reaches its peak, right? Because it's like where the slope is 0, so it'd be in between where it's increased and decreased. So I guess it'd be a local maximum.
Yep. So let me get the graph of this. If I was to graph that equation. It's graphed in here, so. But yeah, you could put it in the calculator or graph it. Find it. Here it is. So this is the graph of it.
Okay.
And so, yes, you can see that that maximum power is when RL equals RS. So graphing this equation right there, this is the same equation. And I can see that when that RS equals RL, it will be at that maximum. And that's where we're aiming to do this. Yes.
Is the RS on plus RL cubed on that?
So here's cubed. Wait, where?
Yeah, right there.
Yeah, it is a cube that I crossed out. Yeah, so that's just combining to get the common denominator. And so the first one, the 1 over RS plus RL squared, I just have to multiply the top by another RS plus RL on the top and bottom, which was a 1 there, and then I can add those together. So it would be RS plus RL cubed on the bottom.
Why are we taking the derivative with respect to RL?
Because that's our load. So we're wanting to know the maximum power to the load. So that's why we're differentiating it with respect to RL. If I was trying to find the maximum power that I would transfer to RS, then I would do it with respect to RS. And that would give me the maximum power transfer to this component here. But because we're doing it, we want it over the load, which is what we're adding on. We're doing it with respect to RL. Does that make sense? Okay. All right, other questions? Okay, so now let's move to complex. So in the complex domain, we're going to kind of do the same thing. So here we have now that Z is complex. It has a R component and an imaginary component X. And so when we find the complex power, we're going to use that the complex power definition, 1/2 V times I. And V in this case is Z times I. And so IL in this case, we have BS over both complex plus JXL and VL So when we plug this in, so I'm missing. Okay, yeah. So when I take the average, well, these are just written out already. So in the S and the average, I'll just, it's already written down here below. I forgot I wrote it in here. Okay, so IL is equal to the VS, ZS plus ZL. And then we want to find the average power. And so the average power is going to be the 1/2 the magnitude of I squared RL. And that's going to be the complex conjugate. And so this gives us VS squared RL over RS plus RL squared plus XS plus XL squared. And then we want to find the same thing as we did before, which is to take the derivative with respect to RL and set that equal to 0. So if I set this equal to 0, whoops. Let's copy it. Oh, sorry, this is not the derivative. Like, wait a minute. This is the derivative. So taking the derivative of this and setting this equal to 0. These are going to cancel, and then I'm going to be left with all of this. And then if I look at So we have two components here, RL and the XL. So we have of that load. So we also need to look at the partial derivative of the XL, which is this one, and set that equal to 0. And so we have these two equations. What?
No, so
So then this will give us, these will all cancel and we'll be left with minus 2XS plus XL equals 0. And, oh, wait, sorry, the minus 2 can be canceled out too. So XS equals minus XL. And then I can use that to plug in here. And then solve this one. And this one ends up giving me RL equals RS. So maximum power will be for the complex will be when RL equals RS. So that's similar to what what we found before for when we just had RL only. And now we see that it's going to be XS is going to be just equal to a negative XL. So that means that the imaginary component is just the complex conjugate. So we can rewrite this as simply just ZL needs to be equal to a ZS complex conjugate. So that makes it much easier. So from this, we can then plug that into the power equation. When the ZL equals ZS complex conjugate, and that gives us this value of the average maximum. So now we want to use this on an actual circuit. So to find the maximum power, we want to choose what load will give us the maximum power from an already designed circuit. So to do this, we're going to first find complex Thevenin. And then from there, we're going to find that ZL will equal the complex conjugate of that ZTH we find. And that will give us the value. And then we can just use the equation for power. And then we'll find the magnitude value of, use the magnitude of the VTH that we find. And that will give us the average power maximum for this. So we're going to set this up to find the Thevenin equivalent. And this one has a dependent source in it. So to find the Thevenin, the first step is to take off the load. Oops. And put A and B and find this VTH this way. So as you guys have seen, I like to do node voltage. So I'm just going to call this V1 and this V2. I'm going to write the node voltage equations. So I like to set my ground at the bottom, so I'm going to put B to be the ground. And then I'm going to write these three node voltage equations. So what's this one? Okay. And this one? And then the top one? So A is just a wire, so I'm going to go back to the node, which would be V2. So I would go V1 minus 2I minus V2. Because the A is just a node in there floating. So this one is going to be minus 2I minus V2 over everything in that branch, which will be 4 plus 6J. You guys follow that? Okay, so when I do node voltage, it's at extraordinary nodes. This node here is an ordinary node. So the extraordinary nodes is V1 and V2. So my branch is everything in this is a full branch. And so it's V1 minus the next node, which would be V2. And then I also have the current or the voltage negative 2I over all the resistors.
Is it because you're finding Thevenin, essentially, like, what you're doing right now is not necessarily finding the voltage at node A. You're basically saying that between A and B, it becomes an open circuit, so that if you follow the current, it moves from V1 past that 4 ohm resistor, and since A and B is a short, or excuse me, open, current's just going to keep going back to V2. Is that essentially kind of the logic?
Yep, that's exactly the logic.
Okay.
But wouldn't it be a voltage source and current source is like the 2I right there in VT panel? You want to do a supernode?
So a supernode is in between two extraordinary nodes. And this one is between one extraordinary node and one ordinary node. So this side of it is also an ordinary node. So I could say that the voltage here is V2 plus 2I. But it's, yeah. I don't know how else to explain that one. All right, so then we want to write a node voltage equation for V2. So I notice that this is also the same as I. So what is my I going to be here?
2 over minus J. Minus J.
Okay, or I can write it as JV2. And then the equation, what equation? Two equations. I'm going to write that same, I can write it JV2 or V2 over minus J. And then what's this one? And then this current.
This is V2 plus 2. Minus J.
Yep. And then I have I, And so I want to know VTH. So if I know the current in this branch, I can do a loop for V1 through that 4 ohm resistor to VTH. And so my loop would be from this node to ground is a plus V1 minus IX4, and then here would be a minus VTH. Or I can do the same thing and do node voltage again and define that IX equals V1 minus VTH over 4 and solve that to get either one of those to get VTH equals V1 minus 4IX. So once I find, or sorry, where did I? IX is V1 minus VTH over 4. And then plug this in and I can get VTH. No, that's just going to cancel it out. VTH is V1 I am drawing a blank for a minute. Find VTH. Oh, yeah, yeah. Sorry, this is not IX. So that is IX, but that's gonna just cancel itself out. So I want to take the current in the whole branch. So it's V1 minus 2I minus V2 over 4 plus 6J. And then I can plug that in here. And get VTH is V1 okay, that gives me 4 V1 minus 2I minus V2 4 plus 6J. And then multiply it by 4, yeah. Okay, so this gives me my equation for VTH. And I don't love complex, so I jumped to MATLAB. So I already wrote a script to copy this and put it in the notes. So I just combined this into a matrix. So I combined all of the V1s together. So for this first one, there's a V1, V1, and V1. So this is 1 plus 1 over 2J plus 1 over 4 plus 6J. And then I combine the V2s. So I have a minus Anyway, you write this out and you can use MATLAB. And we'll go over the results of this next time.
So they didn't take the request. Because they said I didn't fully make it, you can actually send an email to the teacher too. Because it's
Yeah, this is the one you need to get the teacher.
because I talked to Jeremy. I told him all about it. He was like, we still don't know. So it's kind of confusing.
Okay, and then when the check comes, sign up. You're higher, there should be no. Okay, yeah. So you'll just have to wait
Or
until.
do you think I should send an email to this person? So then I just explained something that, and then let's see if they request.
They won't approve it till after Rachel. That's what students do. So you'll have to wait till the end of the semester and then hopefully there'll be still a spot.
If there's not a spot, then you tell
Yeah, then we'll have to look at,
them. But I would rather have it all set up.
and if you take in 3810,
I'm taking that.
so it was 3810 already, 3700. So yeah, we might have to look at like a technical elective if 3500 is not an option.
The reason why 35 is kind of important is because it has the prerequisite for behavior.
Yeah, oh, I know, it's definitely preferred, but I think we can still figure it out to keep you on track if you can't get in there. But hopefully,
I'm thinking about just sending this person an email regarding the situation and see what she says.
you can, I think she'll go off what Jim said and they'll wait. Like they won't reverse it
Just because their
until.
reason
Rachel
is just
goes.
because I'm not considered major status yet. Just because.
Oh, yeah, so let me, I see, yeah, let me send an email. And then I'll send you, just checking on my major status, and then I'll send you an email explaining like, we can't change you to major status. You qualify for
You wanna
major
send-
status. Yeah, and then you can send that email to Teresa.
So I should send an email. So sorry, this is not this. So I said this to